Like pretty big. It's like the map. Yeah, we have like 3 blocks. Yeah, how you can really grab it. Like me frustrated. That's really entitled. On the weekend, and she had her kid with her the entire time. One with her. No, I know, but I'm just saying, like in general, just like working, but I was. You also have the series. I think like the yeah, it's like it's like there's something but you have series like a syringe pump. Yeah, syringe pump. We have a syringe pump that doesn't work. I don't know one upstairs where it's stones. Is it the KV scientific? Yeah, I think we have the same. Yeah, I've been wanting to get one for a long time. It's so expensive. Yeah. And the other one, yeah. Like with the flow rate, what's made like an RPM. Yeah. Oh yeah. Well, yeah. When you do that, never talked about yeah, I might. I don't know. On your own time. For the. Is that like the great Iraq? Like this, I didn't hear anything about it. What did you say? That's what you're yeah, he's generous that he's during all if that goes there, I'll be so they right. I think the way back, like I'm a lawyer. No, I said Argo, I might tell you. And then he's here on that. He's got so many. He gives so he need to go online first here. Right. It'd be nice to go. I'm looking at pay like but yeah. No, I know. Recently, at least 4 years.
Then what I am higher life already started 5 yeah, that's
So you listen to our consulting. Let's do that's why. Next, you're probably get that. Oh yeah, you notice it. I was good last week. So yeah, this off that I requested month ago. Madison and I have so we go to Vancouver at least once a year. So we never go like I'm stuff from I learned that apparently up in a small town. I get it. Me especially way too connected to especially family, but also friends. But like, if I ever did move as a reason, like I love it. I tried, but yes, yeah. They tried it. Yeah. Rest stops. Our friends they're experienced in those areas. So no. Yeah. I was calculate realize They are food fish. They're trying to get around it.
Yeah, I kind of say, I'm really excited.
What you doing, everyone? Or do you have? Yeah. The best you have last. Glad I didn't send you. Welcome to this afternoon. One of the questions that has come up a lot throughout the talks that we've seen, both last term and this term, is the question of climate change and how that has implications for a lot of the design parameters that we use in our sort of more strict definition of civil engineering. So today I've brought in Dr. Xuebin, who's one of the leading climate scientists at Environment and Climate Change Canada, to talk about this very topic. So we're absolutely excited to have you here, and thanks so much for coming, and look forward to your presentation.
Okay, thank you very much. Can you hear me from the back? Okay, I don't usually, talk in an actual hall, so maybe I'm just not loud enough, but if you don't hear me, feel free to wave your hand, I'll try. Yeah, it's quite exciting to come here after a few years, especially after this pandemic. I did give a civil seminar a while ago, invited by Visa. And I have quite a few friends in this place. So when Bin told me, well, would you be able to come here and give a seminar? I say, wow, why not? It's really cool to come here to get myself connected with old friends and also with new friends. So I'm going to talk changes in precipitation, what we know and what we understand. This is a kind of topic that we ask ourselves a lot. Part of that is from an engineering perspective, we use a lot of concepts like design precipitation. And a part of that is there are lots of things with regard to damages like impacts like flood. And I'm not going to talk about drought. That's another kind of structural extreme that we don't have enough precipitation. So here today, I'm going to talk more about what do we think the precipitation that can potentially cause damage. This is a kind of a part of the general subject that we work on with regard to helping engineers to design the buildings or other kinds of highways and so on for the future. I was involved in the National Research Council's work, trying to revise national building codes, highway codes, and a bridge code, so that the new codes in which we will release in 2025 will include consideration of climate change. So up to now, all our building codes and so on do not have the provision that provide guidance for engineers how they should do when they in terms of changing the climate, how they consider that kind of thing in their design. The talk I'm going to give today is a little bit broad. It's not exactly getting into how we do design, but it's more general. And I'll give you some ideas about from climate science perspective, what do we really understand? What do we see from the data? And what do we understand from a physical perspective? And then at the end, I will give some general ideas how what we can do about this kind of information in terms of real world applications. And this last bit part is something new in terms of if you heard my talk before in this general area, because now we actually have much better confidence in providing advice as to how we are going to deal with this. Rather than how we say, yeah, we know something, we don't know something, but I think now we actually know sufficiently well that we can provide clear guidance. So that is my introduction part. Then I look into some kind of physics that warming and increase in extreme what the kind of where the connection we can establish. And then I will explain what we see in observations from both in Canada and also globally. And then I will walk you through about how we understand what are causes of this kind of observed changes. And then I get into the implications of the change in precipitation, and finally give us a quick summary. So I'm going to give a couple of introductions. examples. One is the hurricane hazard. Many of you may actually know. And I don't know if anyone actually experienced it. I mean, I didn't because I came here too late. And then I will talk about the BC flood that just happened a year ago. It caused lots of damage. And what is the implication? What we can actually we can see or we can know from the data from the model simulations. What do we learn from them? And then I'll talk a little bit about managing impacts of precipitation, especially from a change of design value perspective. So hurricane hazard occurred in October 1954. That was I was not born. I also was born in China, so that's why I say I was not experienced on this. So October 15th, 1954, this hurricane hazard hit southern Ontario with 110 kilometer per hour winds and over 200 millimeter rain. This 200 millimeter rainfall would normally not a huge problem, but that particular event occurred at a time when soil was quite saturated, which means when you suddenly have this kind of amount of rain drop into a place, it becomes instant flood, and the water is just too much that to be drained from the rivers. And the storm was really bad. It killed more than 80 people, and many families the homes were destroyed. A big part that if you know Toronto area, if you go north, like even Lake Simcoe area now is pretty flat land. That become a huge lake. So people learned from that disaster. After that, it was the development of weather warning systems and also conservation authorities. Like Toronto, like a different kind of river conservation authority was essentially established after Hurricane Hazel. And this is the older picture that I found from the internet that actually shows where the house was completely flooded away. Last year I was in that area. There's a memorial in that area. I was interviewing someone from working with the weather network. They want to do a documentary. We went there and I saw that the memorial. It was really telling. You know, you suddenly have the feeling of the damage, and you saw that kind of still there's a half of the bridge that was damaged, but still there. You get the idea how much the damage was. But this is a more recent event that occurred just last year. Well, not last year, more than a year. It occurred in DC area. It was hit by 40-hour rain, which is I think it's more than 200 meters bigger than what we had in Hurricane Hazel. Damage was very significant. This is just one little picture that you see. The road was closed, railway was closed, and even the pipeline was kind of shut down. So it was a huge disruption in that region. And now the engineers in DC, they are rebuilding it. And one question they face, what I'm going to do? How big, how much kind of the risk I should take, or what is the in engineering world, what is the design value I should use for the future? So this is something that people are working with we don't know that. A big part of that is the Pacific Climate Impact Consortium that they work with the high authority fairly closely on that question. So a way that we manage impacts of precipitation in engineering, you are engineering people here, so you know more than me. Even though I had a small training in engineering, but I don't claim myself as an engineer. I never practice that. So one of the things that we actually use is something called intensity duration frequency curve. This gives us an idea about the magnitude of rain we get and how frequent it is, and also the time duration of that event. This tool represents what is available from Environment Canada publication is the past climate, because we say, okay, this is calculated based on the data we have, and a consideration about how this kind of curve might change in the future. that has not been published. But we have developed guidance on how to deal with this kind of question. I will explain that later. So now I'm walking through a little bit of basics. The first is that human influence has resulted in warming. This is the thing. If you heard about the statement just given by the Secretary General of the United Nations 2 days ago on Monday, you will get an idea where we are now. We are living in a crisis of climate change, put it that way. And that is due to the human emission of greenhouse gases. And the second thing, which is much easier to understand, is warmer air can simply hold more moisture. This is fairly simple physics. And the reason for that is when we have more moisture in the air, with air start to go up, it just simply get more fuel and produce a heavier rain. So in a relatively simple way, we can think about that. Warmer air will give us more moisture, and as a result, really extreme precipitation, which is the most efficient way of rain that give us stronger rain. So this is a slide that shows something very basic in that human influence has resulted in warming. If we look at the history of the past of the global temperature of the past from 1950 to 1900, no, from 1950 to up to now, we see that temperature has has increased quite a lot since 1900. And this increase in temperature that we observed has not been occurred for more than 2,000 years. So it's not just what we are saying here. It is for many, many years. And what we can see is that if we only consider the natural variation of the climate, that you might be able to see from this kind of flat curve, so that the climate and temperature that's being affected by changes in the solar radiation or by volcanic activity, that is what we get from this flat curve. But only when we really take climate, only when we take human emissions of greenhouse gases into consideration, we start to really see a fit in terms of global mean temperature when we compare with observations in the model simulation. In that, observed changes in temperature, observed increase in temperature can only be reproduced if we take human emission greenhouse gas into consideration. So this is a simple equation. Many of you are very familiar with this, that saturation Phenom pressure is for the exponentially increasing function of temperature. So it follows this equation. Essentially, every 1 degree increase in temperature at this kind of climate translates into about 6 to 7% increase in Phenom pressure. That translated into the increase in specific humidity. So more moisture in the air results in heavy extreme precipitation. Water vapor tends to increase at this rate. Global precipitation, the total precipitation, is affected more by the energy balance. That is, the latent heat released during the condensation process needs to be balanced by long wave radiation cooling. And that rate is smaller compared with the CEE rate. It's only about half or even a little bit less. So when we look at changes in total precipitation, it is about 3% increase per 1 degree temperature increase over the globe. But extreme precipitation is more affected by availability of moisture, as mentioned earlier, because when the extreme precipitation occurs, it is time that you really have the maximum efficiency. And changing hydrological cycle will differ in different regions because of climate, also because of land surface processes and so on. So I'm going to give you some general picture about changes in extreme precipitation that has been observed in Canada and that has been observed globally. So this is a very old paper that when I just started my career with Environment Canada, we look at changes in heavy precipitation at the time. That was 20 years ago, more than 20 years ago. In general, at that time, what we found was that total precipitation increased, but part of that increase is really due to the increase in number of days with precipitation. It's not about changes or in the intensity of precipitation. And at that time, we actually see some kind of small decrease in the rate of precipitation, which means, and also at that time, we didn't really see any kind of clear evidence of increase in extreme precipitation. That was what we did 20 years ago. And then later on in 2014, a fellow working in our group, Michael Shepard, looked at short duration extreme precipitation. He took data from tipping bucket ring gauge. If you know that kind of event, it's a kind of a ring gauge that can accumulate amount of precipitation for different kind of time intervals. It's like accumulation that's been recorded in a curve on a piece of paper. And from there, we can actually know the rate of precipitation from 10 minutes and to 24 hours and so on. So that gives us an idea what the maximum precipitation in a year has been for different time period, which is very important for engineering design. So we look at annual maximum rain for different time duration, from 5 minutes, 10 minutes, 15 minutes to 24 hours. That was what Mark did at the time. And so the message from there is that we didn't really see much evidence of increase in short duration precipitation at local or station level. So if you see here, you really don't see many kind of triangle that shows significance statistically. But there was some kind of pattern of different regions. And essentially what Mark was able to see is in 2/3 of regions, big regions of Canada, there was increase, but the evidence was pretty weak. And more recently, my colleague Alex Cannon, some of you might know him, did revisit what Mark did, and he essentially repeated the work, but with new additional data. Stations are more or less the same stations, but now we have like a 20 more years. Let me see. Yeah, it's we have 20 more years data both in more recent, and also they were able to extend to the earlier time period. So what Alex was able to see was that more stations showing significant trend. We didn't really see much significant trend, but more importantly, increase in short duration precipitation actually quite consistent with what one can expect from the CC relation with regard to the increase in dew point temperature. That is also related to increase in temperature. So essentially what Alex was able to tell us is that with some kind of additional data for which we have, the interchange gets stronger, and we also have bigger samples, which give us more power to actually see changes, significant changes. What he was able to show that, yes, now we actually have clear evidence that short duration in Canada has increased. And that kind of increase in terms of month is consistent with what we would expect from changes in the climate or from warming in temperature. So that's what we saw from Canada. And then when we look at globally, this is a work that a postdoc who worked with myself in Francis Spears published a few years back, was that over the globe, if we look at changes in maximum one day precipitation over the year, we actually see that many places have increased trend. We also see some places with negative trend, but overall, the number of stations showing increasing trend is about twice the number of stations showing decreasing trend. But more importantly, stations that are showing significant increase in trend is way bigger than what we could expect from random noise. But the number of stations showing significant decrease in trend is just about what we would expect from random noise. So from there, we concluded that there was a significant increase in annual maximum 1 day precipitation of global land areas. And this kind of increase is significant in all continents that we have sufficient data. We are not able to really say a lot in regions like in Africa and in South America and so on, where typically data coverage is much poorer. This is one of the quite important piece of information used in IPCC 6 assessment that I was proud of it. So now let me switch a little bit to the causes, to understanding what have caused this kind of changes. I will go through first over bigger areas over global land, and then I talk about what we see for North America, and then what we actually can say about changes or any kind of climate change impact on the BC flood. So over global land regions, when we compare observations, here is the RX 1 day is annual maximum 1 day precipitation. We compare observations with model simulations that consider all external forces. That includes human influence like greenhouse gas emission, aerosol emission, and also natural forcing, natural external forcing. That includes volcanic activity and solar radiation changes. So this is, so we compare observations with what we call all forcing. We also compare observations with the model simulated response to greenhouse gases and model simulated responses to aerosol and model simulated responses to natural external forces, and that is volcanic activity and solar radiation. So what we found was that human influence, in particular greenhouse gases emission, is likely the main driver of the observed global scale intensification of heavy precipitation land regions. So this particular paper was done by a fellow, a PhD student in Korea. But we also had 2 earlier papers that we published. One was published in Nature in 2011, and then a couple more other papers using different methods and different data set. So overall, with all this kind of studies, we were able to conclude that human influence is actually detectable and attributable to the as the cause of the increase in extreme precipitation of global land regions. If we look back into what happened in North America, so my colleague Megan Cashman Young did quite marvelous work. Here, Megan compared observed extreme precipitation, observed change in extreme precipitation of North America in different parts of North America with model simulations, with different model simulation on different external forcing. And what she was able to tell us was that anthropogenic climate change has contributed to the intensification of continental and regional extreme precipitation. And additionally, anthropogenic influence, if you look into the future, will lead to more frequent and extreme precipitation in our region. So if we look at the flood situation, what happened in the BC in 2021, we need to look at that a little bit differently. Here, we only have one particular flood. So we don't really have a lot of in this kind of extreme precipitation on a single location to look at it. So, so this is in the way that we examined this was something called event attribution framework. Here, the idea is that instead of looking into the long-term trend, we try to ask the question, what the probability for this kind of event to occur with or without human influence? This work was done after the event, after that flood event. Especially we got an order from the top that we got to understand what was causing that and how much human influence might have contributed to the change in this kind of a flooding situation. So we organized quite a few people within Environment Canada and also universities in the West, as well as the provincial government people. We worked together to come up with a relatively quick study that we were able to publish, and we were able to advise local government about the rebuilding effort. So what we were able to say was that human-induced climate change is estimated to have increased the probability of precipitation event as large as observed by about 40%. So because of human influence, the precipitation of that kind of magnitude in that region has increased by about 50%. And but when we look at the stream flow, we look at the peak stream flow, that damaged road, damaged bridges, and infrastructure and so on, the change in the probability for this kind of stream flow is not the same as the changes in the extreme precipitation. The estimate was that for quite a few areas with a peak flow from anywhere 50 years to 200 years in that region, the increase in the frequency of stream flow of that kind of big stream flow was about anywhere between 2 to 4 times bigger. So that gives you some idea that what used to be 200 years event now become 50-year event. So you get some idea that if you have some kind of infrastructure that is designed for 200 events, it will fail because it's not that anymore. So I'm going to talk a little bit about future changes and implications. So the first is that we learned quite a lot that the connection between the amount of moisture and the temperature, and then because of that connection and the implication on extreme precipitation. So I'm going to talk a little bit about scaling with global warming. So how extreme precipitation may scale with global warming. And then I'm going to discuss a little bit about uncertainty at local and regional scale. It is local and regional changes that really matters to our day-to-day life, to our adaptation effort and to engineering practice. And then I'm going to talk about recommendations that we made through the Canadian Standard Association's guidance document. But finally, something which I think are very, very important, caveats. So what we really know and what kind of things we still don't know, and when engineers use that kind of recommendation, what aspect they really need to pay attention to. So this is a work that been done by a guy who used to be also with us at the PK with myself and Francis. And here, what he did was to estimate changing in precipitation in relation to global mean temperature. So you look at for each model simulations, you get long-term changes, you get time series of global mean temperature. At the same time, you also are able to collect extreme precipitation at different locations. And by estimating the changes at different locations related to global mean temperature, putting together, you get some ideas about how extreme precipitation at different locations might change with temperature. So because we really don't know what the future may look like with regard to the emissions, so we look at different emission scenarios from something which is really, really mild in the sense that very, very aggressive emission reduction, that is SSP 2.6. This SSP 2.6 roughly translates that we could meet 1.5 degree Paris Agreement. And then we also look at changes in a very more like a business as usual SSP 8.5 that translates to 8.5 watts per square meter increase by the end of 21st century due to the human emissions. And that is really, really business as usual. But if you think about all the policies being implemented by different governments with regard to emission reduction, that's probably not business as usual anymore. So it will be something I don't think we actually will hit. But then there are also 2 other scenarios in between. So what he was able to show us is that regardless the model, climate model that's being used, regardless the emission scenarios being used, in general, there's about 7% increase in extreme precipitation globally with 1 degree temperature increase of the globe. And this seems to be quite consistent across models, across scenarios. So the increase when we think about the intensity increase, with more linear with temperature, and if you are interested in the frequency, in the change of frequency, then you get the idea that the change in frequency will actually not be linear with the change in temperature, because when you think about the probability distribution, the change in the location and the change in the cumulative probability are different. So what we really are interested in is at regional and local scales. And if we think about at different regions, the increases in intensity of precipitation at regional scale can be different, and depending on the amount, regional warming, and all changes in atmospheric circulation and storm dynamics. But overall, as a bigger picture part, it's about 7% increase per degree temperature increase. So this is again a work that was done by Charlie, and here what he was looking at was changes in extreme precipitation as simulated by Canadian regional models of Region 4, RCM4. So here there are different. Okay. In this way, if you look at here, this is the changes in between temperature, and this is a relation, or what we call the scaling, that amount of changes, the median value of changes in extreme precipitation per degree temperature increase over North America. This part is calculated for one simulation, and this part is calculated for another simulation. And then here on the top is calculated based on time period 1951 to 2015, and the lower one is for the future period 2036 to 2100. What we can see from here is the picture is very noisy. So that's the first thing. The picture is very noisy. You can see, and all are different. And the second thing is that even for the nearby pixels, they may show a different sign. So what it really tells us is it's not this is useless, but it's just noisy. What that means is that if we just pick up a particular location and try to calculate how changes in precipitation, it's not going to tell us a lot about what has happened. It's also not a good guidance for us to use that to extrapolate towards the future. But this is what is really meant here. So we need to have better way to quantify changes in extreme precipitation and try to remove this kind of noise as much as we can. I'll get to that. The spatial consistency. I have the slide later on. So, but if we repeat this kind of calculations for many model runs, we actually can reduce this kind of noise to show that some kind of smooth picture, which I showed one slide later. And that's the kind of things we use as a way of guidance for the engineering design. Now I get to what we have recommended for the engineering design. That is, we documented in the CSA guidance documents called CSA plus 4013 in column 19. I don't examine, it's a kind of document number. So this is a technical guide for development, interpretation, and use of rainfall intensity, duration, frequency information. So there, what we recommended was that increase design precipitation by 7% for 1 degree projected increase for a particular region or particular location. If you are in Toronto, or if you are here in London, you can use your current climate, add about 7% more for the future time that you know temperature might be. What that means is that by if you think about your structure will be designed, will be used by 2050, And we get some, we actually have pretty good idea by 2050. In our area, temperature increase will be maybe around 4 degrees. So you are looking at 27-30% increase. And if you look into more remote future by 2100, then it gets much more complicated. In that, because we don't know what the human society will do with regard to climate mitigation. We don't know if 2100 will give us temperature by 7-10 degrees here or by only 6 degrees. Really depends on not only our behavior, but the behavior of the entire world. But then engineers are experts for risk management. So for something that you feel that should be important, like this is my hospital, I'll do everything to protect it, you might just design at a very, very high level. But if this is something like a shopping mall, you know it will be gone because of whatever internet. You probably can lower your standard for that. So that's a part of risk management business. And the reason for that is when we look at changes over the big region, we actually see that it's mostly consistent with what we call the CEE relation over the space, over entire Canada. This is something that we actually have a common to say, because when you look at the small regions, small scales, the signal noise ratio is just so small that to the point that we have lots of uncertainty. So it's actually the bigger picture that help us to have the confidence to say, okay, this is the number that I should be using. But on the other hand, we do see that in some regions, like in this kind of big regions, the increase in projected precipitation, extreme precipitation, is smaller than 7% increase relative to their regional warming. So then when we come to the engineering exercise practice, we will need to know, engineers will probably need to think about, okay, if I'm in this region, should I be really using 7% or smaller numbers? I think it will be their judgment. Again, is part of risk management business. Yeah, maybe I feel more confident or I feel more comfortable to use smaller values. Or maybe they feel this is important, I just use more conservative, larger values. So really depend on the actual context of the design or engineering. So when we talk about this 7% increase, we are really not talking about some other kind of things, such as tropical cyclone. And so lots of things that are happening in the country or the land regions are really about convections, about big storms, or even in BC, it's more about atmospheric levels and so on. But there are things which can actually bring us bigger change that is especially affecting Atlantic region like tropical cyclone. Of course, it can also affect our region. I mean, Hurricane was initially a tropical cyclone and become actual tropical cyclone here. And I believe the precipitation that brought to us from the Hurricane Hazel are still being used as a design precipitation in many different kind of process. Lots of PMP calculations or probable maximum precipitation calculations, at least in terra regions like in our area, in Toronto area, but still based on this kind of Hurricane Hazel. So it doesn't mean that tropical cyclone is not very relevant even to our region. So the tropical cyclone, we have evidence from model simulations that the tropical cyclone, extreme precipitation brought by tropical cyclone can increase beyond 7% per 1 degree because of stronger convection, because of some kind of changes in the dynamics. And more importantly, when we think about tropical cyclones now and in the future can actually survive into much northern regions compared with in the past in the warmer climate. That means that the kind of tropical cyclone we didn't have in the past can actually come to us. And the tropical cyclone in some regions can actually move even slower. And that also means that if it stay there for a little bit longer, it just gets more precipitation. So that's getting much more complicated. So this is another kind of area that when we do engineering, we need to think about the guidance, what the caveats that need to be taken into consideration. And the last part I want to talk about is uncertain part is being specifically asking me, what about if people asking me to do 700-year return value estimate is there uncertainty? How can I trust that? So I'm going to talk a little bit about it. This was done by a professor at the PK called Phenom. Some of you might know him. And he gave a presentation at the multi-hazard workshop not long time ago. So we know that when we fit extreme precipitation to extreme value distribution, it's a fairly common practice to extrapolate to a much longer return period. Say if we have 50-year data, if we try to calculate 50-year return value, 100-year return values, that kind of calculation comes with uncertainty. That kind of calculation comes with uncertainty. So the longer the return period is, the bigger the return, the uncertainty in the return values. That we know very well. Simply because we are extrapolating towards the future. But this kind of uncertainty can be quantified. We can quantify that uncertainty. We know how big is the uncertainty. If our data actually follows the kind of probability distribution we use. In general term, that kind of probability should be good because there is some kind of statistical theory called max stable theory. I'm not going to get into detail about that, but the general assumption is that, okay, as long as you have data sampled from the eye, it should converge to that. That's the theory. But in reality, in situations that we have with the data we have, the extreme precipitation may be caused by different processes. I mean, think about that. If you have data that's been sampled in a really short period, mostly from convection, but suddenly have some kind of huge big ones that due to hurricanes. They do not come from the same processes. They are not from the same family. So when we put them together, they may not fit, which means that the theory itself may fail in this kind of situation because that's not considered. So this is exactly what Phenom found for that. So in some regions, extreme precipitation does not converge to our theoretical distribution. In that case, it fails. What it means is that this is based on the model simulation for which we have many data points. We have many years. We have 1,000 years so that we know what happened. But in any kind of individual simulations or like observation we have, we are limited by 50 years, maybe 100 years. We never know this could happen, which means that if we try to extrapolate our data towards the future, if we try to think about 700 or 1,000-year return values, we don't really know where we are because, okay, it could be that we are very well behaved. I mean, data well behaved. That could be somewhere here within this kind of bound, which we know we can quantify the uncertainty, but it can be well above, or well below. So this well above and well below are just the kind of things we don't really have a good means to handle because we don't have the data and we don't really know exactly the process underneath. So now I'm concluding my seminar here. So a few messages that you can think about it. The first is extreme precipitation has intensified on global, continental, and regional scales. And over Canada, we are now seeing clear evidence of increase in short duration extreme precipitation. Human influence, in particular greenhouse gases, is likely the main driver of the observed global scale intensification of heavy precipitation in land regions. We found it's actually not just on global scale, but also on regional scales in many regions. Anthropogenic influence will lead to more frequent intense precipitation extremes. There's really no question about for this particular conclusion. That's what we said in the IPC6 assessment. We have very high confidence about this. The extreme precipitation scales with the level of global warming, and the scaling is independent from emission center and first order approximation. This is actually quite useful for us when we think about what the future may look like, even though we may not be able to quantify at any individual location precisely, but this can serve us as some kind of general guidance. So design values for long-lived infrastructure can be guided by scaling relationship, but the level of uncertainty in future projection is high. And this is really the area that the attention needs to be paid. And when we use something, we cannot just take the data, or in fact, for the future, we don't have the data, we don't have the observations. As granted, we already ask ourselves the question, how much I can trust it, what are physics, what are kind of things, what are theories behind it. In terms of the guidance that we provided through CSA, it's not just about model simulations. It's about all the evidence that we have from observations, from understanding of the cause of Chinese precipitation, and also the projection future. So a lot of things that come together give us the confidence to provide that kind of recommendation. I stop here and thank you very much. I'll be happy to take questions.
Thank you so much for sharing that with us. Are there any questions from the audience? Yes.
You refer to a lot of predictions based on your models. How do you verify that these predictions have any value or they have some accuracy? How do you verify? How do you trust these predictions?
Okay, so the models have been verified in all sort of ways. So, well, you have the observations. So you can verify it through the cometology. You can verify it through long-term changes.
But you do like simple problems. You have observation from a year ago and what happens today. You run simulation from a year ago until today, and what you predict is what you actually observe.
No, that's not how we actually do it, because in the models, you reproduce the physics, similar observations, but because of chaotic nature of the current system, you cannot reproduce the daily sequences. So it's not like you're saying, okay, what happened yesterday, I will be able to reproduce exactly what is going to happen today. I mean, from a model, but we can verify in a different way that the statistics, the general properties, and so on. So it's not about actually reproducing the sequences, which we can never do because it's just chaotic system that does not represent.
But when you get situations of today, you can integrate your model back in time and find out range of conditions that could lead to what we observe today. It's a kind of a simple way of verifying.
Yes or no, depends on what you define observation actually.
Well, it's common sense. You give me weather.
I think this might be better for an offline discussion. Are there other questions?
Yeah, sure.
Thank you very much for your presentation. So my main question is regarding the uncertainty one that you have by, like in your models, you have what people want there. So we are going to give the results to the practitioners, like the policymakers for the data design level. We're going to introduce them to designs with this, huge amount of uncertainty. Isn't it better to use a regional climate model for this every region to lower the amount of uncertainty?
It's if you look at this, the uncertainty is not. It's not always the case. You can actually load uncertainty. It's simply because the change is still relatively small compared with the natural variation. So if you use like very high resolution model of a very small region, you probably can only produce relatively limited amount of integration for the years of the data, and you're not able to really figure out all kind of noise. So what you see will be will not necessarily reduce uncertainty. There, with regard to uncertainty projection, there are certain elements that we can reduce, but there are also elements that we just cannot reduce.
Yeah, and like the global climate models, GCMs, cannot capture all the climatological events. We know that they cannot capture the extreme precipitation, convective precipitation, or even the tropical cyclones that you showed. So my question is, how do we rely on these models when they cannot capture one important source of precipitation, which is convective precipitation?
Let me see. So this is the kind of way we look at it, and there are also regional models with very high resolution regional models like convecting commission model that Limping has quite a bit of experience on that. And there's also simulations being conducted by people like Inca and also Europeans and so on. So the overall thing, when you look at all this kind of evidence, it gives us something similar to this in that precipitation increase with close to CC rate in many situations. So the kind of things we say here is not purely based on global models. Global model give us some kind of big picture, but when it comes to the overall conclusion, that was just one source of evidence. There are other evidence that point to something similar.
Thank you.
Okay, I think we're almost out of time, so we'll let everyone go for the next class, but I believe Dr. Zhang will be here after the presentation for
Yeah, be happy. Yeah.
any discussion afterwards. Thank you all.